So chapter number 11, we're starting with 11.1, physical properties of group 2 metals. As you already know that we refer to group 2 metals as alkaline earth metals. Wherever for a group we use the word metal, it means all the elements in the list are metals. Wherever we use the word earth, that means they are taken out of earth's crust. And if here we are using the word alkaline, that means whenever they react with water, they produce tightly alkaline substances. So for group 2, they have the electronic configuration that end with two electrons in their outermost principal quantum shell. For example, this two or two, you'll see the same thing at the ends of all of these. So the two electrons occupy an S subshell of whichever principal quantum shell that they are a part of. Moving on, beryllium, magnesium, calcium, strontium, barium are actually elements of group 2. Moving on, the way of describing the size of an atom is its metallic radius. The metallic radius is half the distance between the nuclei in a giant metallic lattice, and this is a very good way that it has been represented. I hope with this you get an idea what the R stands for or the metallic radius stands for. Now, since they are all metals and since they are present in the giant metallic bonding, so I think metallic radius from a giant metallic lattice is the appropriate thing to do. Moving on, for group 2 elements, as you can see that the metallic radius increases down the group, starting from the least value for the top of the element and moving all the way to the maximum value to the bottommost element. Okay, since we're discussing up till barium, that's good enough, and the trend goes in the same way. Nanometer stands 10 raised to power minus 9 meters, and all the metallic radii have been given in nanometers. Radium has not been discussed over here, being radioactive. Moving on. Now, if you look at the atomic numbers and you relate it with the melting points and densities, you get an idea that the melting points are decreasing down the group with, of course, an anomalies of um, first two elements, beryllium and magnesium. The rest goes in appropriate way of decreasing down the groups. For densities, you will again notice that the second two elements, 1.74 and 1.55, is different, and then they are increasing down the group, which for every group they should. Now, if we look at melting point, this actually becomes the habit of it. Now, this seems really fine. What this seems is a little bit odd. Now, let me tell you before we move on to any other groups, usually the top metal or the top element of the group is a little bit different from the rest of the group, and the anomalies are always discussable. As for density goes, yeah, this is completely understandable. Again, density is supposed to increase from top to bottom in a group for the whole periodic table, but group one and group two are actually an exception to it. Group one has been discussed really in a good detail in back in ICCST or O levels. This is the point where we discuss group two as well. Moving on, right? Okay. Reactions of group 2 elements. The group 2 metals form ionic compounds. When they react, their elements lose two electrons from their outermost subshell, form an ion plus 2 arrangement, stable arrangement because of an electronic configuration of a noble gas. The plus 2 ions are actually common with all the elements in group 2, so that goes from beryllium all the way to barium. Their metals act as reducing agents. The more reactive they are, the better they are at reducing agent work. Now, their atoms donate or give away electrons. They are oxidized themselves, so they react to form plus two ions. The ionization energies are shown over here, which gives you a pretty good idea that when we move from top to bottom in a group, the first ionization energy decreases, which actually is also an identifier of why they become more reactive going down the group. If we talk about the second ionization energies, it would give you a similar trend. The second ionization energies also decrease down the series, down the group, which gives you a pretty good idea. Now let's discuss the reasoning. Since we have discussed the reasons for ionization energy before, this should seem familiar. This shouldn't be seem difficult or different. So the metals in group 2 get more reactive as we go down the group. As you can see from table 11.3, the values are decreasing from top to bottom. So it takes less energy to remove a pair of outer electrons, going down group 2. Although positive charge in the nucleus increases down the group, the greater shielding is provided by extra inner shells of electrons, and the distance of outermost electron from the nucleus actually outweigh the nuclear charge increasing factor. So these two factors outweigh the nuclear charge increase. So I hope you understand why it still keeps on decreasing for that matter. So this helps us to explain the increase in reactivity going down the group because it is easier for the atoms to become plus two ions. The group 2 elements get more reactive down the group, an important part, something that I've repeated a couple of times, so it shouldn't be difficult. So moving on, trend is shown by if the reactions, the chemical reactions of group 2 metals. I hope you do understand that we have discussed different types of reactions for group 1, so we can do the same. Back in IGCSE, the reactions that we commonly discussed was the reaction with oxygen in the air, the reaction with water, or usually the reaction with a dilute acid. So starting off from the same in the same footsteps, I think it's easier to understand that if we are talking about reaction with dilute hydrochloric acid, forming a salt giving off hydrogen gas should be something familiar. And if you take a look at these reactions for magnesium and calcium, the reactions get more vigorous descending down the group. So calcium is, of course, going to give you a more vigorous reaction as compared to magnesium for that matter. So magnesium reacts in the similar way with dilute sulfuric acid. However, any reaction with calcium, strontium, or barium is quickly stopped by the formation of insoluble sulfate layer on the surface of the metal. This is important. Now, since these are not exactly insoluble, so the reaction keeps on going. This is also not insoluble. The reaction keeps on going. This is insoluble. This actually stops the reaction. And he says the same thing with calcium, strontium, or barium, because all of them are insoluble. You already know about calcium. Strontium wasn't discussed much in IGCSE, but barium BaSO4 is something been very specific in IGCSE for its white precipitate. So I hope you clearly understand this. To be honest, CSO4, SrSO4, or BaSO4 all are white precipitates. And these precipitates are insoluble sulfate layers in the surface of the metal can definitely stop the reaction. For example, if you see a slow stream of hydrogen bubbles for a short time when a pellet small piece of calcium atom is dropped into dilute sulfuric acid, the calcium then gets completely covered by a layer sparingly soluble calcium sulfate, and of course, the bubbles of hydrogen stop rising from the metal. So this gives you the idea that if forming an insoluble compound or salt may interfere with the reaction. So strontium sulfate and barium sulfate are even less soluble than calcium sulfate, so will quickly stop any reaction with the metals strontium and barium. So group 2 sulfates get less soluble going down the group. This is something that has been important. Among the important things written on in this whole portion, this has been used most in the past papers. Okay, so also the group 2 solubility of sulfates is something that you need to remember for AS as well as for A2. You'll see that this specific point, this specific part that I've discussed, has also been a part of A2. Keep this stuff in mind. You're going to use it for a longer duration of time compared to the rest of the stuff in this chapter. So 11.3, reactions with oxygen. As I've discussed earlier, this is something we do back in IGCSE. So hopefully most of the things that we face in here are going to seem familiar. So group 2 metals burn in air. They burn more rapidly in oxygen gas. They form white solid oxides. but the flame color is something that is important when we discuss it over here. Magnesium ribbons burn with a bright, white, flashy flame when once ignited in Bunsen flame. I hope you're familiar with the reaction of formation of oxide. Magnesium oxide is basic in character, so we can dissolve it in water. It's a little bit soluble in water. It gives in slightly alkaline solution with not very high of a pH, but definitely more than 7, and it's also considered as milk of magnesia. I hope you remember it that we have also discussed it as a remedy for uh, stomach acidity or indigestion. That was a part of IGCSE previously, so everything over here related to this one can be easily be considered as a prerequisite. So group 2 metals get more reactive with oxygen going down the group. The larger atoms lose their outer two electrons more readily than the smaller atoms in the group. So the reasons are something that we have previously discussed. I hope you have done this easy and fun experiment with your hands before. Now, barium metal is so highly reactive that it must be stored under oil to keep it out of contact with air. This works just like the group 1 elements, alkali metals, because most of them are so reactive, they keep on reacting with oxygen in the air or water vapors in the air. So we store them under oil to keep them out of contact with air. Just a minute. So some of the group 2 metals burn with characteristic flame colors. In the heat of Bunsen burner flame, the metal atoms are oxidized, losing two electrons, forming their positive ions. The oxidation number of metal atoms, of course, increases to the plus 2 state. Oxidation occurs. The plus 2 ions formed in the reaction cause the characteristic colors. For the flame test, I hope you remember well from IGCSE that calcium gives a brick red color, strontium gives scarlet or red color, or barium compounds give an apple green color. Now, how do we test those colors in a flame test? Flame test will be specific over here. We use a nichrome wire. This is a nickel chromium alloy nichrome wire. You may use a platinum wire, but since platinum wire is absent in most of the schools being very expensive, we try to go for nichrome wire. That is cleaned with concentrated hydrochloric acid, is dipped into a sample of the salt to be tested and heated with a non-luminous Bunsen flame. A non-luminous Bunsen flame means the Bunsen flame needs to be blue in color before you test it for any flame. So I think this blue part and this upper area gives you an idea about the brick red, the scarlet, and of course the apple green color. So moving on, reactions of oxides with dilute acid. The basic oxides of group 2 metals can be neutralized by acid. Since they're basic oxides, they're going to react with an acid just like base does, neutralizing it, forming salt in water. So MgO, as an example, reacts with HCl. It forms a salt in water. In the similar way, any oxide of this group 2 metal will react and would neutralize an acid. Now, the white magnesium oxide powder dissolves, forming a color solution of magnesium chloride. As it reacts with the dilute acid, the oxides of CaO, SRO, BaO are also neutralized by dilute hydrochloric acid. A similar reaction occurs when excess dilute sulfuric acid is added to group 2 oxide, but a sulfate solution is forming. And the sulfates, for the sulfates, we've already discussed that their solubility is something which is actually discussable at this point. So magnesium sulfate is soluble, but if we talk about from calcium to barium, the solubility decreases greatly, so they're not soluble. So decreasing solubility of sulfates forming going down the group will also affect the neutralization reaction with dilute sulfuric acid. The insoluble sulfates will form at the surface of the oxides, protecting any solid oxide beneath it. So when this happens, actually they tend to stop the reaction. However, when the oxide is in the form of powder and stirred, significant neutralization can occur, right? So I hope you understand how sulfates and their solubility is going to affect any kind of reaction. So reaction with water. Now we have seen enough in section 10.3 how magnesium reacts very slowly with cold water. However, if left long enough, the reaction will eventually form a weak alkaline solution, magnesium hydroxide, given off enough hydrogen to test. So we can actually collect it after a longer duration of time to test it. And of course, I hope you remember the test for hydrogen and the pop sound. Okay. So hot magnesium, however, does react vigorously with water in the form of steam. So in this case, the basic difference between this reaction, you're going to consider this one as cold water and this one as steam. That's where the basic difference lies in the reactants. And of course, products are totally different. We are not talking about the hydroxide anymore. It produces an oxide. Calcium reacts more readily with water than magnesium at room temperature, so we do not really need to heat it up. And this is going to give a steady steam of hydrogen, and it forms a white, cloudy white suspension of slightly soluble calcium hydroxide. Calcium hydroxide that does dissolve forms a solution that we call lime water, which makes the solution peakly alkaline. Now, going down the group, hydrogen gas is released more and more rapidly by the reaction of group 2 metals with water. Barium's reaction is even very vigorous when it comes to that. So, a reaction showing magnesium reacting with steam. The steam is given off from the mineral wool soaked in the water at the right hand end of the test tube. So, the white magnesium oxide forming is visible inside of the test tube. I hope you get it. The hydrogen gas produced in the reaction has been ignited at the end of the straight tube. So you can see the flame coming out of it, giving you the idea that producing hydrogen gas. So yeah, it's easily understandable. So barium reacting vigorously with water, forming alkaline barium hydroxide solution and giving off oxygen gas. Okay, so reactions of group 2 oxides. But before I go with this, uh, take a look at this diagram and the bubbles and where the bubbles are getting originated from. Now, I'm going to take you back to a point where they have discussed some information. This question is more related to the densities. That's why I'm scrolling back to the table where we had the densities of these. Okay, take a look at this. These are group 2 elements and their densities. Now remember, when we were talking about group 1 metals and their densities, I told you that the density of pure water is around 1 gram per cubic centimeter. Okay, so the alkali metals used to react vigorous or violently with water, and they tend to float on the surface of water, produce hydrogen gas, which usually got ignited at the end. Of course, the hydrogen can easily catch fire and turn into a flame. Now, since the elements, group 1 elements, were like zero point 0.5 or zero point 0.4 or zero point 0.8, whatever the exact values were, I'm just giving examples, gram per centimeter cube, they were always lighter than water in terms of their densities. So what they used to do was to float on water, turn into a molten ball. That ball usually caught flame because of the hydrogen being produced on reaction with water, and that's how it happened. You can always look up at YouTube the reactions of alkali metals with water, and every time you'll see that the elements tend to float on the surface of water. This is because of the low density in water. Take a look at these. You'll find that all of them have high densities than water. So they won't tend to float on the surface of water. And that's exactly what I was trying to show you. Having a higher density than water, gives barium a chance to sink down at the bottom of water. And that's where the source of hydrogen bubbles of hydrogen gas originate. And that's you can see over here. So it's not floating on the surface of water like group 1 alkali metal does. Hope you get an idea in the difference, and you will be able to solve MCQs related to it. Although there are rare MCQs, but there are MCQs related to this one. So reactions of group 2 oxides in waters. Magnesium oxide, as I've already discussed, is only slightly soluble in water, so forms a weakly alkaline solution of magnesium hydroxide. A saturated solution of magnesium hydroxide would have a pH value of about 10. Calcium oxide reacts with water to form calcium hydroxide. When water is dripped on the surface of a lamp of calcium oxide, it causes a vigorous reaction. It releases so much energy that the sum of the water boils off as the solid lump appears to expand and cracks open. So for this kind of experiment, we tend to go with a teacher's demonstration. In IGCSE, at A levels, we always ask our students not to go with this reaction in a huge amount of water. Drops of water will do the trick, since this can easily burn you if you use a little bit more amount of water. This reaction has to be extremely cautious, so keep that stuff in mind. This actually works well for paper three, since there are points in paper three where we are supposed to go with this reaction. Now, in excess water, some of the slightly soluble calcium hydroxide dissolves to form a weakly alkaline solution, give way with a slightly higher pH than magnesium hydroxide. So the higher concentration of aqueous hydroxide ions turns the pH to about 11. And instead of 10, we have somewhat a little bit of a higher pH. Okay. In general, the reaction in which group 2 elements, oxides, are converted into this is this one. This is the reaction because of which the oxides of group 2 are actually for being converted into hydroxides. And that's how they turn up alkaline and give us a pH higher than 7. So the solution formed from the reaction of group 2 metal oxides with water get more alkaline down the group. So I hope we understand that this reaction is more easier if we go from top to bottom in a group. So we can explain this increase in alkalinity by even looking at the solubility of group 2 hydroxides formed. If you take a look at the group 2 hydroxides formed, you will see that the solubility of hydroxides is actually changing and is increasing from top to bottom in a group. Okay, so the same thing is mentioned over here. Therefore, when adding and stirring magnesium hydroxide in water to make a saturated solution, then doing the same with barium oxide, there will be higher concentration of hydroxide ions in POH twice solution, of course. The higher concentration of hydroxide results in a higher pH for BOH oxide, BaOH twice as well. Okay, so reactions of hydroxides with dilute acids, it's pretty easy. A hydroxide is actually more like an alkali, so it reacts forming salt and water. This should be easy how they're going to react and form salt and water. Now, since to be very specific about sulfates, the more we go down the group, the more insoluble a sulfate becomes. So that's why you can see aqueous, 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 and solid. That's the difference for these equations. So this one is, since a solid and insoluble is a white precipitate. So I hope we understand it. Since we have worked a lot with barium sulfate in previous portions, IGCSE, this shouldn't be a problem. So next up, reactions of group 2 carbonates. Now, the group 2 carbonates have the general formula of XCO3, X, or sometimes we write it with M, since there is just one ion of the metal and then there is CO3. That's because the metals usually end up with plus 2 ions. CO3 has a negative 2 charge. So this tends to cancel the charge and we end up with MCO3 or XCO3 for magnesium, calcium, strontium, and barium. And their carbonates are all insoluble in water. So yeah, I hope you understand this. This was mentioned back in IGCSE too. So I hope you already know about the carbonates. So the carbonates all react with in dilute acid, forming a salt and water, giving off carbon dioxide. I hope you remember from IGCSE, whenever carbonate salts react with an acid, it produces a salt, it produces water, it produces carbon dioxide. We used to actually take this as a test for carbonates because they used to produce carbon dioxide. We used to further test carbon dioxide with lime water. The lime water turned milky. So this was taken as a test back in IGCSE. So magnesium sulfate salt formed in the reaction above is soluble in water. This remains in aqueous solution and no solid carbonate will remain in excess dilute sulfuric acid. However, the sulfates of group 2 elements are much less soluble than magnesium sulfate. Remember the decreasing trend in solubility. We have discussed it before. So if even if magnesium sulfate is soluble, as we go down the group, barium sulfate tends to become a completely insoluble sulfate. So sulfate layer on their solid carbonates will tend to form. for calcium, strontium, and barium. This stops any further reaction after the initial bubbling of carbon dioxide gas is seen. For example, this happens in case of barium. So the reactions of group 2 carbonates with dilute hydrochloric acid will all form soluble chloride salts. So in those cases, you will never be able to write this as or talk about any insolubility. Okay? So thermal decomposition of group 2 carbonates and nitrates, something we have discussed as a part of IGCSE. So let's revise quickly. Carbonates can be broken down into oxides and carbon dioxides. So we, since are doing it on the basis of heat, so the term thermal decomposition, the temperature at which thermal decomposition of group 2 carbonates take place increases going down group 2, which means it's easier to break magnesium carbonate, but it would be difficult to break down barium carbonate. So the group 2 nitrates also go under thermal decomposition. This usually results in formation of an oxide, nitrogen dioxide, and oxygen. So brown gas, nitrogen dioxide is observed, nitrogen 4 oxide, of course. As with the carbonates, a higher temperature is needed to thermally decompose nitrates as group 2 is descended. So it goes the same. Since the explanation of this trend, thermal stability, is a part of chapter 19, which is A2. So we only go with what the trend is or how this reaction goes in thermal decomposition. We do not actually discuss the detail of this trend because the explanation is a part of A2. So apart from this explanation, just the trend itself or what the reaction is going to produce is a part of A2, is a part of AS, sorry. So that actually finishes the chapter. Any questions?